f of x is given here, and we're told that the equation f of x equals 0 has a single root alpha. I'm asked to show that it lies in the interval 3.6 to 3.7. So what we're going to seek here is a sign change. We're going to look at 3.6, and if we can show, say, that it's negative here, and then at 3.7 it becomes positive, or vice versa, then if the function is continuous over the interval, it must somewhere in between hit the x-axis, and that would be our root. That would be when f of x equals 0. We just have to convince ourselves, actually you get away with it in this question, but that there's no discontinuity, because you can get a sign change if something just jumps from below to above, such as with 1 over x. Just be aware of that one. There would be a sign change, but there wouldn't be a root. Now for tan half x, I'm going into a little more detail than is needed here, but remember tan x looks a bit like this, and you get a discontinuity at pi over 2. This is a stretch in by factor 2 in the x direction, so the discontinuity here is going to be at pi, and then the next one on would be at 2 pi. So we're okay. We're like looking in this realm here, basically, for tan half x. We're absolutely fine. Let's get on with it. So now I'm going to find out what f of 3.6 is. My only other thing to say before I substitute in is make sure your calculator's in radians. You can see they've implied that with the interval of x up here. So I'm just going to go with, yeah, let's just do 3.6 equals. That will store it as my answer button. And then I can do answer. I mean, maybe this is unnecessary, but answer plus tan 0.5 answer. Of course, you can just type in 3.6 if you prefer. And this gives minus 0.686, which is less than 0. And let's find f of 3.7. So this time I'm going to do 3.7 equals, and now this really comes into its own because I can just press up and get the same thing back and just do it really quickly. That's why I did it this way. 0.2119, which is greater than 0. So just need to say we have a sign change. And this is very important to say this, and f of x is continuous over the interval. So alpha lies in the, I was going to say between, but I'll say exactly how they've written it in the interval 3.6 to 3.7. Good. Now asked to differentiate f dash x, differentiate x to give 1. Now tan, if you look in the formula book, differentiates to sec squared x. So you can quote that. Just got to use the chain rule here because I've got a half, or you might just have learned that when you have like a kx, you just times by k. Fair enough if you've learned that. But we're going to get 1 plus a half sec squared a half x. It's going to be our answer. Then we're asked to use 3.7 as the first approximation in the Newton-Raphson method. Here is the Newton-Raphson method. I always like to remind people what is actually going on in the Newton-Raphson method because it's easy to like teachers to talk about it and then you just kind of forget and you just end up substituting this formula without having any idea what it's doing. So I always think we want to understand it along the way because there will be questions potentially that test our understanding. So let's imagine that the graph is looking a bit like this. Now in the Newton-Raphson method, we put a first point in and we find the value of f. This is what this iteration formula does for us. We don't have to worry about it. And then we find the gradient of the tangents, which is where that denominator is coming in, and we just then follow it along. And we hit another point, which then becomes our new approximation. We do the same again, and well, in this case, you very quickly converge towards the root. So put our value in, get our value of our function, follow the tangent along until it hits the axis, do the same again, and we're going to get the root. Obviously, the closer you are to the root, you're quickly going to get there. It's going to depend on the shape of the curve because if you can basically, if you start in the wrong place, you can end up kind of going all over the place. That's just what's happening. Now we just need to be able to apply it. So for us, we've got xn plus 1 equal to xn minus, then I'm going to be putting my function in, so it's going to be x plus tan of a half x, but actually now it should be little n's there because these are part of my iterations. And then the derivative that I just found was 1 plus a half sec squared a half xn. We've got x0 equal to 3.7. That's my starting guess. And we're just asked to apply it once. Okay, let's go for it. So we've got to be like really careful typing this in. So I'm gonna use the answer button. Just good to get into this habit. 3.7 equals, because if I did want to iterate many times, this is the way to go. So then it's going to be answer. Just replace all my xn's by answer to get the next value. Because what I'm doing here is substituting in n equals 0. So x1 is going to equal x0 minus, and then I replace all my xn's by x0s. And if I wanted my next iteration, I'd let n equal to 1, then be x2, and then in terms of x1. Okay, this one here, right, just got to really carefully type it in. So this is going to be answer plus tan of answer over 2, or half answer, however you want to do it. Then 1 plus. Now I think this is the trickiest bit. So I wrote a half. Okay, and I'm timesing by sec squared. Now that is 1 over cos squared. So I'm going to write it as a fraction, I think, just to be careful. And then to do cos squared, we're going to need, well, I think it's best to put brackets in. Cos, and then it'll be answer over 2 again. And then I'm going to close that bracket. I probably could have got away with not even putting that bracket in, but I think it's good too. And then I'm going to square it. Okay, that there will give me a half sec squared, a half xn. Press equals 3.67205. 3.6720. And it's to 3 decimal places. I just wrote it to a few more, well, 0.5. So it's going to be 3.672. And what is worth doing, just to kind of check we've done it right, is to actually, even though it hasn't asked us, just do a few more iterations now. So now answer is this. If I press equals, I'm going to be putting it back in and getting a new value. And you can see we very quickly converged to a value. If it had sort of jumped all over the place, I'd be starting to question, have I put it in wrong? Because that sec squared in particular could cause some problems. But this is actually going to be, the root to say 8 decimal places. Well done.